All right, so new topic today, class. Let's talk about motion.
Wow, are we in physics?
Yes.
This isn't physics anymore.
I haven't
That should play your theme song.
I haven't taken physics.
Oh no, we're not in calculus.
Oh my. All right. I don't know what you're
Oh
referring
yeah, I can pull it up right now if you want.
to.
The end of our physics.
So, oh, that thing.
Are you gonna show them that?
Maybe.
Oh my gosh.
Oh my gosh.
I watched it. They're gonna come up just and be like, you guys are so
Wait,
crazy.
who was it? Me, you, and Fun?
I purposely said don't make it cringe, and yet you all made it
Well,
as
I did it
awkward as
cringy.
possible.
On purpose, especially the last part, just to really get to them.
Hey, I think
Make it-
ours was gold.
It'll
Right.
connect.
Yeah, you didn't yell it like with like the wind was blowing.
Yeah, you
loud.
couldn't hear y'all.
Oh, hi.
And then,
Wait, what did you say? It's like, I didn't see anything.
and then y'all were like running around and fighting each other. And I was like, what's going
Wait,
on?
and then my superhuman strength with the car.
Oh yes.
That was
I was there in person for filming. All right, so here we go. So, believe it or not, calculus was made because they didn't have the math to do the physics. And by they, I mean Newton, Sir Isaac Newton. So he's like, I need to solve these problems,
So we
these
can
motion problems, and so he made calculus. It's pretty cool. He discovered it. So what we're gonna do is we're gonna talk about motions. We're doing it sort of backwards. I'm teaching you the math, and then we're saying, and this applies to physics. We really should do it the other way around, but we don't have time for that. So let's go ahead and talk about some of these things that I'm sure will not be new to you, but we're going to go through it anyway. So in discussing motion, there are three closely related concepts that you need to keep straight. They are the three things that you need to describe anything's motion, and that is position, velocity, and acceleration.
Didn't we talk about this yesterday?
We did, so that's why I'm not going to write all the other junk that I normally write right there. So I will write x of t or s of t. We'll see that. V of t, which we did say is the derivative of position, and acceleration, which is the derivative of velocity. All right. Maybe we can see how well we can do this without me having taught it. So here we go. If x of t represents the position of a particle along the x-axis at any time t, then the following statements are true. Initially means when blank equals 0. T equals 0.
Oh yeah, it could be time.
This does not want to play along with me here. I'm not sure what's going on. So yeah, that's initially means when time equals 0. At the origin,
is position.
Position.
it says at the origin says nothing about time, so it's just position.
Okay.
Yep.
Mm-hmm.
It doesn't have to go through the origin at time 0.
At rest means
She has World War
And
II.
we're not
E
playing along.
equals 0,
Talked about
right?
it yesterday.
Yes.
We were really just talking
What
about
if it
it.
isn't crystal?
About why
All right, hold on.
It's really, it looks really good.
So-
The graphics are.
Let me play it.
All right, so initially means when time is 0. At the origin
I asked for it for Christmas.
means x equals 0. At rest means it's not moving.
B.
The velocity equals 0. That's right.
No, no, I'm doing this.
So if the velocity of a particle is positive, then we say the particle is moving in the positive direction. We've described this entire situation. We're only going to be talking about something that's moving back and forth on a number line. We're not going to be talking about something that's moving, in both the x and y direction in a parabola. Okay. We could refer to something that's moving up and down. However, right now we are limiting ourselves just to the x-axis. And on the x-axis, that's the positive direction. This is the negative direction. So if the velocity is positive, then the particle is moving to the right. To the right. If the velocity of the particle is blank, then the particle is moving to the left.
Negative.
Negative. find the average velocity over a time interval, divide the change in blank by the change in time. So average velocity is delta blank over delta t. And y'all are saying x? You're correct. It's the change in position by the change in time. So that's for the average velocity. Let's put a note off to the side of that number 6. If I had a graph of my position, okay, so I'm going to put x up here and time right there. This is the position versus time graph. Alright, we can make this simple. I'll have my particle start here at the origin, and it's going to start moving to the right, okay? And then it's going to go faster and faster and faster and faster. So that graph might look something kind of like that. Would you all agree with that? Starts off at the origin and it moves faster, faster, faster. What does delta x over delta t look like to you?
What do you mean?
Like, what is that?
Like,
We've seen that expression before, that quotient.
oh, like,
Okay, we call that the derivative. Although normally that would be the derivative, you're thinking more like dx over dt.
yeah, like slope.
Yeah, this is more like the slope, okay? And if we're actually saying delta x and delta t, we're talking about measurable quantities. So, for instance, yes, the secant line. Delta x over delta t. So the average velocity is the slope of the secant line between 2 points. So if you had some graph and it was showing you for how many seconds, and I said, what's the average velocity for the first 3 seconds, then I'm saying average velocity, that's here and stuff like this. However, if you've ever been in a car and you've hit the accelerator, which is kind of like what this is, right? And you look at the speedometer, it starts off at 0 and it goes, 5, 10, 20, 30, 40, 50, 60, it's going up like that over those first 3 seconds. Well, if you get 0 to 60 in 3 seconds, that's pretty good, okay? So what we could also talk about, though, is what we've been dealing with all year round, or long, is the tangent line. And the slope of the tangent line is what we have here in number 7, the instantaneous velocity. That's the velocity at a single second. Okay? So that would be as if you were looking at the speedometer and seeing exactly what was it pointing to right now. How fast are you going? So this car might have a very, maybe this is going over the first 3 seconds, its average is 30 miles per hour. Let's get some, the velocity average is 30 miles per hour, but at a given point, like right here at the very end of it or close to the end, the instantaneous is more like 60 miles per hour. Does that make sense? If you would take those first 3 seconds and average it out, you're going to go 30, but that's only because you've got some high numbers up here, like 50, 60, 70, and some low numbers here. So if the acceleration, looking now here at number 8, the acceleration of a particle is positive, then the blank is increasing. So remember we said that you've got position, velocity, and acceleration. So if the acceleration is positive, then the velocity is increasing. If the acceleration of a particle is blank, then the object is decreasing. The velocity is negative. In order for a particle to change direction, the blank must change signs. Velocity, because remember, positive velocity means you're moving to the right, negative velocity means you're moving to the left. So, Mission, watch me and see what has to, call out my velocity, positive, negative, or zero. Okay? Can you do that for me? There you go. Call it out. Just, it's always the same number line as always. Just give me a positive, negative, or zero.
Or negative.
Like just like a number line. Negative.
Positive.
Oh wait, I went from negative to positive. Okay. Y'all help me out. Call it out here.
Positive. Negative.
No.
Positive.
Negative. Okay. If something goes from positive to negative, what number does it have to go through?
Zero.
So call out zero when I'm zero.
Oh, okay.
Wait,
Negative.
where's negative?
Zero.
Zero is when you
You're
turn.
saying, where's negative?
Where
Zero
is
is when you
zero?
turn.
It doesn't matter. I don't care where zero
Zero's
is.
It's
where
when
you
he switches sides.
Like, yeah.
Hold on.
When he's turning.
When he's
Aha! Got you. That's what I was hoping to do.
Or
All
not
right.
when he's
I'm sorry, I haven't finished physics yet.
No, that's fine.
I'm
There's
still in physics.
This is something we have to address, okay? This right here is zero. On the number line, okay? But, so x equals 0 means at location 0. Velocity equals 0 means not moving. Okay? Now, where does velocity equal 0 have to occur? It will occur at maximum, yeah, relative maximum. But what I'm gonna, does my not moving, does that have to occur at the origin? No. I could be over here in positive territory. My position is positive, but my velocity is 0. Okay? I could be over here in negative territory, just hanging out. My position is negative. My velocity is 0. Okay? So, once I start moving in this direction, what's my position? Negative.
Where's the origin? Right
Origin is this bar right here. Okay? Katie, what's my velocity? Positive or negative? It is, because I'm moving in the positive direction. Jesus, what's my position?
Positive.
Velocity.
Positive. Oh, well then.
Okay, Trey, what's my position?
Negative.
Velocity.
Negative.
What's your acceleration, sir?
We'll get to that in a second. Okay. Cammy, position. Velocity. This way. Position.
Negative.
Velocity. All right. So positive. So just call it velocity. Velocity is
Positive. 0. Negative.
There we go. Yes.
Can I use some of your overhead earphones?
Oh, okay. Yeah, sure.
He's about to game.
All right. So the idea is, think about it like this. I'm going negative velocity. So negative. So like heading off in the negative direction here. Negative velocity, and then I slow down to 0 in order for me to turn around. Okay, and it goes positive. Okay. Now, let's talk about acceleration. Okay, acceleration can be positive or negative. All right. Acceleration means a change in velocity. And acceleration is one that everybody gets mixed up on. Okay, so what does acceleration mean equals 0 mean?
Velocity is constant.
My velocity is it's not changing. Okay, so let's see if I can do this. Do I have acceleration? Why not?
You're speeding.
Not speeding up or slowing down. So my acceleration is 0. What about now? Still 0.
But when you turn.
Okay, well, I'm gonna deal with certain situations first. Katie, is that good for you?
Yeah.
0 acceleration. Alright, one of the big things is that when something equals 0, it means it's a different thing in each case. So position equals 0 means you're at the origin. Velocity equals 0 means you're not moving. Acceleration equals 0 means your velocity is not changing. Okay? What about right now? What's my position? Mission?
0 or
What's my...
3.
Okay, yeah, about 3. Okay, good point. Good point, yeah. Keep going. Mission, what's my velocity?
0.
Acceleration.
0.
Ooh. 0 acceleration because I'm not moving, right? Alright. Now, I'm going to go through the 4 situations between velocity and acceleration. Okay? And I could have velocity is positive and acceleration is positive. Velocity is negative. You might have this on your paper there somewhere. Acceleration is negative. I could have velocity is positive, acceleration is negative, and velocity is negative, acceleration positive.
So what are those like what would you call them?
I call this the 4 scenarios for velocity and acceleration. Alright, I'm going to start over here. 0 is a good place to start out. Somebody tell me, we're going to go through first scenario 1, positive velocity, positive acceleration. Positive velocity, positive acceleration. What should I do? Go that way.
And
Accelerate.
And now this acceleration is positive, which means my velocity is increasing. Okay, so here I go. Positive velocity, positive acceleration.
Whoa.
Run into the wall.
Got it?
Run into the wall like the guy from the.
Yeah.
Yeah. So if I were to draw what's called a motion diagram, I would draw arrows going to the right and getting longer. I'm going to start out over here because it's a lot more fun. I'm going to do the other basic example. Negative velocity, negative acceleration. Now negative acceleration means that velocity is decreasing. Okay? Now I'm already getting negative velocity. So I've already got like -5 velocity. So if I'm at -5 and I'm decreasing, what does that mean?
your speed
You're-
in the negative direction.
The
Decreasing
negative
means going more and more negative. It doesn't mean getting closer to 0. Okay? So if you're at -5 and you decrease, the temperature outside is -5 degrees, and you decrease, what's the temperature? -6. Make sense? That's sort of a mental block I've found with this year's physics students taught me that when I say decreasing, they think gets closer to 0. And if you're in positive territory, that's true. But if you're in negative territory and you're decreasing, you're getting closer to negative infinity. So this is the other, it's the basic example. Negative velocity, which way am I heading, folks, for negative velocity? That way. And I'm already kind of moving that way. Now, acceleration is negative, means my velocity is decreasing. So I'm going from -5 miles per hour to -6 miles per hour to -7 miles per hour to negative.
Oh, you actually ran into the wall.
So, all right.
You can't
Makes
go at
sense.
-7 miles per hour.
Never repeat.
I didn't see it.
Sorry, missed
Did you do
it.
one more time?
No replay on
Just
this
head
one.
first.
So,
You reported it.
You can see
yeah, but I'm gonna.
You can't go -7 miles per hour.
Okay. So there we have negative velocity, negative acceleration. If I were to put a little note here, positive acceleration means that the velocity is increasing. This is a fun thing. Okay. let's deal with this situation right here. Positive velocity. So that means which direction am I going? Going that way. So I might need to start over here if I'm going. But the other part is acceleration is negative. Now that means that velocity is decreasing.
So you slowing down?
Ooh, maybe. I'm gonna start off at 5 since that sounds like a good number. So I'm going 5 miles an hour. Since I'm decreasing, I'm gonna be going now 4 miles an hour, then 3 miles an hour, then 2 miles an hour, then 1 mile an hour,
Start going back the other way.
then 0 miles an hour. Now at that point, if I'm still decreasing, I'm going to turn around and I'm no longer in a positive velocity situation. Okay? So let me say it again. Positive velocity, negative acceleration, which means my negative acceleration, one way you can think of it is I'm accelerating that way, I guess you could think of it. But anyway, negative acceleration means velocity is decreasing. So decreasing velocity. You thought I'm going to stop. So with this diagram, I'm going to start off with a rather long motion arrow, and it's going to get shorter and shorter and shorter and shorter. Yes, you did say, I heard someone say speeding up on this one. Also speeding up on this one. And over here we would say, someone said slowing down. Yeah, that's correct. You can probably guess what this next one is, but let's just go ahead and do it just for fun. Velocity is negative, so that means I'm going to go that way, so this is a good place for me to start. Alright, now acceleration is positive, which means my velocity is increasing. So some numbers that I might have, since my velocity is negative, -5. If I increase from -5, Trey, what's the next number that I'm going to hit?
-4.
-4, that's right. So I'm going -5 miles per hour, -4 miles per hour, -3, -2, -1, 0. Okay? So that motion diagram looks like starting off negative, but it's becoming more and more positive. So there we go. Obviously that is slowing down. In pre-calculus, pre-AP physics, so I'd say more like middle school, junior high physics, you use the word speeding up, slowing down, and that's pretty much good enough for you. Something's either going fast or going slow. But now we're at a higher level of understanding here, okay? We don't talk about speed, okay? Because if I said speed, then you'd be like, yeah, okay, you're speeding. I say you're speeding up. You then say, okay, but you could be speeding up that way, or you could be speeding up this way. You see how the word speed is kind of ambiguous? Speed just doesn't care about the direction, it just cares about how fast you're going on. How fast you're going. Slowing down, if you say you're slowing down, I'd be like, okay, you're slowing down, but give me more information than that. You see what I mean? So, you could say the velocity is decreasing. Although even if you just say velocity is decreasing, well, I've got two situations for that. Alright? Anyway, what I'm getting at is the word speed is not the same as velocity. Okay? Right? Because
You should put a little dot that says not
Oh.
equal to not.
not equal to velocity. What is the relationship between speed and velocity?
Is it like one
The
line?
distance over time.
Just a,
That's you're thinking velocity does equal distance over time, and that's also speed. But we're talking about, look at this, speeding up, speeding up.
velocity gives a quantity
Velocity
of
has
direction.
direction.
Yeah.
Velocity gives and speed just gives the quantity. Okay. So here is the relationship. Speed is equal to the absolute value of velocity. Because think about it in this negative direction. I'm speeding up, right? -5 miles an hour, -6 miles an hour, -7 miles an hour, okay? And so on and so forth. But how would you define my speed in that situation? Increase. My speed is increasing. I'm going faster and faster, okay? So these four situations give rise to the phrase that all physics students have memorized for many years, okay? And now you are going to understand it as well. We say, same sign speeding up. Same sign speeding up. What is that? What do y'all see about that? Sign SIGN.
Velocity and acceleration.
Mm-hmm. Look at that. Negative, negative, you're speeding up. Positive, positive, speeding up. But what happens if they're opposites?
Slow down.
Slowing down. Katie, does that make sense for you?
Yes.
Good. If it doesn't, that's okay. Just ask some more questions. Oh my gosh, alright. All of that, and we still need to deal with number 10. In order for a particle to change direction, the blank must change signs. Velocity is the correct answer there. Because if I'm turning around, that means, think about it, I'm either going from a negative direction to a positive direction, I turned around, or I'm going from a positive direction to a negative direction, I turned around, so my velocity must have switched. Alright? So let's do an example right here. If the position of a particle is given by x of t equals 1/3 t cubed minus t squared minus 3t plus 4, find the total distance traveled. Now this is like, I need to read this part here. One way to determine the total distance traveled over a time interval is to find the sum of the absolute values of the differences in position between all resting points. That makes sense, doesn't it?
Mm-hmm.
Alright, explain that to us, Matthew. To find the total distance traveled is to find the sum of the absolute values of the differences in position between the resting points. Just rolls off the tongue.
Oh, yes.
Go ahead, I'm going to erase this. Teach us, Matthew.
Okay, so the total distance traveled mean, okay, so if you're starting from the origin, you can go both positively or negatively down a number line. However, the absolute value of it would be would make negative positive as well. So it's only measuring how far you've gone instead of in what direction.
Ooh, I
Yeah,
like it.
displacement.
That's a good starting point here. So, see if I understood you correctly, man. You said if you start at the origin
Mm-hmm.
and you end up at +7, what's the total distance traveled?
7.
Okay? And so you start here and you end here.
Yeah.
This is x naught and this is x. So distance equals
7.
7 minus 0, which is 7.
Mm-hmm.
That's the difference of the values of the, what is it, the differences in the position. This is the difference in position. But if I go over here to -7, what's the distance that I've traveled?
7.
Still, I've traveled 7, we know that. But how could I calculate that? Because if I use the same formula final position minus initial position, then I would have final, which is -7 minus 0. -7 minus 0 is -7.
The sum of the
Displacement's always
absolute values.
Ah, so I can stick absolute value bars around that,
Mhm.
and that tells me that my distance traveled is equal to 7. If for consistency's sake, if I put absolute value bars around this,
It'd be the same thing.
it'll still give me the same answer, so that's great. So if, in fact, this is the formula for distance traveled, okay, between 2 points, the distance is equal to the absolute value of your final minus your initial. Great. But what if I turn around 3 or 4 times?
Calculate the origin from the last place you landed.
Mm-hmm. So,
You take the origin
It's still
from,
Where
when you
and your
started
end
and
point.
then where you ended.
so let's say I start here, and then I go over this way 7 units, okay? But then I turn around, and I go this way, and I stop at -4, okay? And then I turn around, and I stop at 10. How far have I traveled?
10.
No. Well,
That's your displacement.
Oh, displacement, no.
that is correct. My displacement, so I want to say, you answered that question, correct? Displacement is, by definition, final position minus initial position.
You
So,
traveled 20.
10 minus 0. So 10. Notice displacement is positive, which is helpful because it also tells me I am displaced in the positive direction 10 units from where I started. Okay? But if I want to figure out the total distance traveled,
31.
32.
let's see. Y'all can look at this geometrically and you say that's 7, and then from 7 to -4, that's
11.
11, and then so from -4 to 10, 14.
So 32.
Okay? Now, the next thing is, can we write that out symbolically? It's obviously three stopping and starting points. So we write the absolute value of 7 minus 0 plus the absolute value of -4 minus 7 plus the absolute value, the distance from here to here, 10 minus -4. Remember, it's the same as always. You always put your ending point minus your starting point. Ending point minus starting point. Ending point minus starting point. And the math works out beautifully. Because this is going to be the absolute value of 7 plus, what's -4 minus 7? -11. 10 minus -4? 14. So I have 7 plus 11 plus 14, which is 32, just like we were able to visually figure out up there. Okay? So, the way that I figure out the total distance traveled, look at it from a big picture. This plus this plus this. That's a sum, right? The sum of what?
Absolute value of the difference.
Okay, hold on. The absolute value
Of the differences
of the
distance traveled.
differences
in position.
and it's the differences of what? And the answer is
In position between the resting points.
of the positions between resting points. Notice, this is a resting point, this is a resting point, this is a resting point. Where did you come up with such a great phrasing there, Josue?
Oh, well, you know, I'm fully surprised to say.
No doubt. That's what the full and complete meaning of this sentence is. The one way to determine the total distance traveled over a time interval is to find the sum of the absolute values of the differences in position between all resting points. You might say, oh my gosh, isn't there an easier way of doing that? And the answer is, not yet. Right now, and I this thing was so annoying to me when I was in AP Calculus, but that I still remember it. That you've got to figure out this and this and this, and you've got to add them all up. Okay, so we've got to play the game. That's just what we have to do. So now this right here is a little bit more complicated than that motion. That guy's kind of went this way, then he went this way, then he went that way. This right here is a graph. Let's figure out what this graph looks like. Grab a calculator and let's sketch that. Is that what y'all get?
Yeah.
Okay. King, yeah. I agree. Now, I kind of want to just, we'll use this whole thing, I guess. We need to find some interesting points here. I think 0, 4, right?
Yeah.
1, 2, 3, 4. Okay. Now, what would probably be good is for us to figure out what does this graph mean that the particle is doing on the number line. Okay. I mean, this is a graph showing somebody that's going back and forth on the number line. Okay. Although we cannot go negative infinity on the number line. Okay. So let's just start off at some time over here like -10, and we'll go from time equals -10 to time equals positive 10. So that's probably what you have on your paper, right?
Yes.
Okay, or on your graph. So here's the number line. This graph right here represents the motion that some particle is doing back and forth here. Does that make sense? So at time t equals 0, so this right here, or not t equals 0, t equals -10, where is the particle on the number line? Negative territory. So, for instance, this dot right here means -10 seconds. And what's that value? Somebody trace that for us real quick. Where? I don't even know if it goes -10. Let's just trace it to the end of visual on your screen.
-198.
Okay, that's a little too far. At the my graph ends at like -3 point something. Okay, so that's what I'm going to put here. So at -3 seconds, this particle is at -7.4. It's around there. All right, so the idea is this graph is showing time and position. All right, hey Susie, with me? So where am I going to draw this on the number line here. At -7, it's starting right there, okay? So this is t equals -3. Right? So then it looks like the particle moves, hits 0, and is moving in a positive direction. So you kind of think of this y-axis, okay, is very similar, is this x-axis. So at time -2, we're here. At time -1, we're here. At time 0, we're here. Does that make sense? So that would correspond to the particle traveling this way, okay? And how high does he get there? Trace that along. How far does he get? Just to give you a ballpark maximum.
5.6.
5, okay? So 2, 3, 4, 5. So it gets to about 5, somewhere around there, and then stops and starts turning around. That's this turnaround spot right here. Not sure exactly where that is. But then he goes back through the and so that's around time t equals -1. Then he goes back this way. Does he go negative?
Yes.
Yep. Looks like he goes negative and then turns around. So he goes negative and turns around. And then he just continues going positive. It's kind of a different way of thinking about this. But maybe just kind of flip this sideways and imagine, 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi. Does that make sense? It's the same thing as going 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi. Alright? So, what they are asking is they're saying find the total distance traveled between time equals t equals 0 to t equals 6. Okay? So on this graph, that would mean find how far he traveled from this point right here for the first 6 seconds. Now what's this x-intercept right there? Around what? 4.4? What about this x-intercept? 1? Okay, so 6 seconds is going to be somewhere around here. What we want to do is we want to figure out how far this object traveled from here and then back around. Okay? And what we're going to do, so we're only concerned about this point right here, from 4. We're concerned, how far did he go this way, then he turned around, and then how far he went that way. Okay? That's what we're going to talk about on Monday. All right. See you then.